Moving on from the last tutorial, we're going to discuss something that is called best compromise infeasible design. This happens when the optimizer realizes it cannot find a solution, it cannot find a minimum or maximum that satisfies all of your constraints. Here in this example, we're dealing with the same surface plot as before. We're starting with the same initial point, but this time we are saying that the solution or the optimum has to be inside of the green ellipsoid and has to be inside of the red ellipsoid. You can see that the optimizer, when it sees this, it will actually try and land in between both of the constraints. The optimizer would then prompt you and say that no solution can be found, but it did find a best compromise infeasible design. So again, we're dealing with the same objective function, x squared, x1 squared plus x2 squared. We're dealing with the same constraint expression, but this time we're going to say that the upper bound is 1. Before it was set to 1. We are also going to set a second expression that you see here defined by G2, and we're going to say that this expression should always be less than 1. In effect, that is creating these two ellipsoids, and it's saying anything within the green and red ellipsoid is a satisfactory design. But here we know up front that there is no solution. So let's go ahead and see how to spot this and catch this in Nastran. So to start off with, in the video description below, there are links to two PDF files. Make sure to download your copies to your machine. And let's start with the web app. Let's go ahead and load these two files to the web app. So I'll go ahead and select the design model PDF and the model PDF file, and then I will upload it. In the previous video, we went ahead and defined side constraints. You can just totally delete these side constraints and ignore it for this example. I believe you can include these in the tutorial and you should still see the same result. Or actually you won't, so make sure to delete the lower and upper bound for x1 and x2 when you perform this tutorial. We'll still use the same objective function, x1 squared plus x2 squared, but now our constraints. We will go ahead and modify the bound for this first constraint. Instead of the lower bound being 1, we're going to say the upper bound is 1.0. We will then go ahead and define our second expression. And for this, let me go ahead and move to my PowerPoint where I have the expression written out. And we will go ahead and look at Notepad and type in the expression. So this will be x1 minus 2.5 squared plus x2 divided by 2.0 minus 0.75 squared. So let's go ahead and copy all of this and paste it in the web app. And like before, we'll go ahead and put in the upper bound of 1.0. So again, these two expressions are defining the two ellipsoids, and since the upper bound is 1, this is saying the solution, the optimum, should be inside of the first constraint and the second constraint. We know up front that no solution exists for this, so now we get to see what Nastran does in this case. Let's go to the exporter and download these two new PDF files. We can delete the old ones, and we'll create a new folder here on the desktop called 2 optimization working directory. We will then go ahead and move those files that we just downloaded, and here in my case they're in the downloads folder. We'll move those to the 2 optimization directory, and we'll start Nastran to perform the optimization. So let's go ahead and click run. And let me show you the diagram while that's happening. Again, the optimizer will make an attempt to go towards the minimum of the surface plot. But then at some point during the optimization, it realizes that there is no solution that is satisfying all the constraints. What the optimizer then tries to do, it will try and land in between the constraints. So let's go ahead and open the file, the F06 file, and scroll to the very bottom. And here, let's first look at the message. Run terminated due to hard convergence at an optimum. And here, it's actually tried to perform an optimization, and now I actually forgot to do something. So let's go ahead and delete all of these files and go back to the web app. I neglected to include this new constraint R2 in the constraint group. If you're dealing with the structural model, you might have multiple load cases or subcases. Once you define your constraints, you have to apply those constraints to your subcases. Here, I have a constraint group that only includes R1. R1 was the first constraint I created before, but I forgot to include R2. So let's go ahead and type in comma R2 here. And now the optimization will include the second constraint. So let's go ahead and download these two PDF files again. And then we'll go ahead and relocate these files to the working directory. And now let's go ahead and start Nastran. So again, what happened a moment ago is I forgot to include the red ellipsoid constraint. So when it performed the optimization, it actually landed here in the middle of the green ellipsoid. But now, since I've included the second constraint, we should expect this message. So let's go ahead and open the F06 file and inspect the very bottom of the file. This time we see run terminated due to hard convergence to a best compromise infeasible design. So I think this is the third time or fourth time I'm saying this. The optimizer realizes that there's no solution, there's no optimum that satisfies both of the constraints. So it went ahead and landed right or almost in the middle. And let me see if I can zoom in on this and show you what the value is. Bear with me while I play with this. The value it landed at is 1.26 and 0.755 with the Z or F value of 2.16. So let's go ahead and see if that's actually the value we got. So here at the very end, it landed at 2.16 and the value is indeed 1.26 and 0.755. You might be asking now, how do you fix this problem? And let's go ahead and discuss how to fix this. One situation where you can encounter this in structural optimization is where you might be trying to satisfy stress constraints for hundreds of structural parts. Such a solution may sometimes not exist. And let's discuss what you can do to fix that. Here is the same example, but you'll notice something different. The red ellipsoid is larger. In fact, the upper bound was changed from 1 and it's now 3. So in effect, that's making the red ellipsoid larger than it was before. And just to repeat, before G2 was set to an upper bound of 1, so that would be this red ellipsoid. Once we increase the upper bound to 3, it enlarges the set of solutions that we can find. In structural optimization, this is equivalent to, say, expanding the bounds of your stress constraints. Maybe the stress constraints were too tight. Maybe it's time to expand those to find a solution. And here, let's look at what the optimizer does. The optimizer will start at the initial point. It will make a move towards the local minimum. But here in the overlap is a set of solutions that satisfies both the constraints. So here what it does, it goes into this intersection, it touches the red ellipsoid, which is the upper limit of that constraint, and then realizes that it can still further reduce the minimum, so then it continues down until it ultimately hits the value of 0.899, 0.178, and a Z value or F value of 0.84. So now let's go ahead and do this with Nastran. So here I'll move the directory to the left here, and I'll create a new one, optimization directory, expanded constraints. So we'll go back to the web app, and for the constraints, instead of the upper bound being 1, we'll go ahead and type in 3 there. And then in the exporter, we'll download 2 new BDF files. These 2 BDF files should be placed in this new directory. And then we'll go ahead and start Nastran and run that new set of BDF files we just downloaded. So we'll click on run. So we'll go ahead and open the F06 file after the optimization is complete, and we'll look at the very bottom and we'll see the result. This time we see a run terminated due to hard convergence at an optimum. This is indicating that an optimum point has been successfully found. Remember that before it said hard convergence to a best compromise infeasible design. But this time, after we made the edit of expanding the constraints, it finally found a solution for the given problem statement. Here we see that it landed at a Z or F objective value of 0.839. And a moment ago, I just showed you that the value is indeed 0.839 here, 0.84. And at the very end, it landed at a value of 0.89 and 0.18 for the x1 and x2 values, which are the same or comparable values that we had here on the plot. So there you have it. That is the situation where you might encounter an infeasible best compromise design. Again, this might happen if you are dealing with a lot of constraints in your model and there's no solution for that given problem statement. What you can do, such as I just demonstrated, is you can expand the constraints so there's actually an overlap where a solution does exist, as I just demonstrated. That is essentially the end of this tutorial. Right now, I could take some time and show you what I have in store for the next tutorial. The next tutorial will involve global optimization. So let me actually give you a sneak peek of that. And first, let me see if I can find the correct file. What happens in the case where there are multiple local minimums or local maximas? What happens in that case? And here I'm just setting this up so you can see what I'm referring to in a moment. And give me a moment while I look for the file. So here, let's go ahead and show you what the next example will include. So here's a completely new example. You can see here that there are 2 local or 2 maximas for this case. We're going to explore what Nastran does for this given example, and this is where we talk about finding the actual global example. So definitely stick around for this next tutorial.